let's get started. So my name's Dr. Paul Connolly. I've seen some of you before. I'm not sure I've seen a lot of the atmospheric programme, so the 3+2, so I think it's the first time I've met you, so hello. And James Allen is away this week. He asked me to fill in for him. So I'm going to give this lecture on the water cycle, and James has put my name down here. They're actually his slides, so he gets to blame. Any questions, you can speak to James about that. Right, so there's some learning outcomes. The intended learning outcomes today, so I'll just read through these, are to, you will be able to, hopefully, at the end of today, you will be able to detail the important properties of water and its important role within the Earth system. So we're going to talk about all of the ways, or a lot of the ways in which water interacts in the Earth system, and also describe the important processes within the Earth system science, including cloud formation, precipitation formation, ice sheet formation, and the transport of other elements by water. And also describe the mechanisms by which the water cycle influences climate. Okay, so we'll talk about some of these mechanisms shortly. Also to discuss the direct and the indirect impacts human activity has, or has had, on the water cycle and any potential consequences. So we'll talk about the impacts that human activity has on the water cycle. And also discuss some methods of so-called weather modification. And I think James mentioned to me that he's been talking to you about geoengineering techniques. Is that right? Yeah? No? Okay, so we'll talk about another kind of geoengineering technique, solar radiation management technique, to do with the water cycle in ways that we can perturb clouds potentially. Okay? So that's the intended learning outcomes. Briefly, I want to talk about different forms of water. So for this course, you need to know, so it's just basics really. So water can exist in the form of liquid water, obviously, water vapour, ice, and biomass is another important source of water. For example, if you think about liquid water, human beings are about 70% water, so it's a significant part of you, me. Hydrogen is assimilated, so there's this chemical reaction here, into biomass during photosynthesis. And we'll use this equation, this chemical equation, in one of the examples in the second part of the lecture. Now what this actually means, it is a little bit ambiguous, so I'll try and explain it a little bit. So we've got CO2, gaseous CO2, plus H2O being converted to some other molecule here, and molecular oxygen. Now what James has done here is he's divided this whole equation by 6. So this molecule CH2O, that's not the actual molecular formula, that's been divided by 6. It's actually approximately C6H12O6, glucose, that we're considering. But nevertheless, the important point with this equation is you take the elemental ratios in this equation. So you can divide this whole equation by 6. The actual equation looks more like, if this works, DocCam, there we go. So it's actually 6 CO2 plus 6 H2O. Gives us C6 H12O6 plus, and what have we got left? 6O2. But for the purpose of this lecture series, we can divide this whole equation by 6, because we're only really interested in the ratios between the elements in this equation. Hydrogen can form part of hydrocarbons in fossil fuels, and it's produced by anaerobic respiration, so you can produce methane by this method. Anaerobic meaning without oxygen, so it doesn't need the presence of oxygen. It's a formation pathway for methane, CH4. And also hydrogen is converted back to water during respiration or combustion or other oxidation processes. Now, I guess those of you who did scientific problem solving, we did an exercise last year where it was called altering the atmosphere by burning fossil fuels. So that was just basically burning hydrocarbons, something like methane, in the presence of oxygen to give CO2 and water. So this is this process here. So James tells me he's talked to you about reservoirs too, the concept of a reservoir. Is that right? Anyone not know about the concept of a reservoir? So we all know about this. So this is just to show you that there's a big range of what we call a burden, the amount of mass, or this is actually volume, which is related to mass obviously, and their turnover times. So how long a typical molecule of water would last in this reservoir before being converted or before being transported somewhere else. So, you know, ranging from the oceans, 10 to the power 9 kilometers cubed, down to biomass, I guess, 1,000 kilometers cubed, with turnover times, average lifetimes of something like 2,500 years down to about 6 days. So it's just a whole range of different burdens and turnover times. Okay, so water's an interesting molecule. It has unique properties due to this bent structure, H2O. It's a very strong, extremely strong electric dipole due to this bent structure, and the electrons around the oxygen atom and around the hydrogen atom. So the electron cloud is pulled away from the different elements in this molecule to create a strong dipole, which can result in hydrogen bonding between the molecules. So intramolecular bonding, not intermolecular, intramolecular bonding. And this gives rise to the different phases depending on temperature and depending on pressure. So we have the phase diagram here. So you can think about the phases of water. You can think about water vapor, and we can think about the interaction, the intramolecular bonding between the water molecules being intermediate. So every now and then there's an interaction, and then a molecule flies off somewhere else. We can think about liquid water, where the hydrogen bonding's stronger, and we can think about ice, where the hydrogen bonding's stronger still. Okay? And the kinetic energy of these molecules in the different phases is different. In a gas, the average kinetic energy tends to be more. Molecules are moving around faster than they are in the liquid and the solid. So there's this phase diagram here. Now, this can be confusing. We've got temperature here, and we've got pressure, which is measured in atmospheres. Now, when I think about pressure, I think about the pressure of the air. I think that's safe to say most people think about that. But this pressure is if we had just water vapor. It's the vapor pressure. So if we had a room with just water vapor, what would the phase diagram look like? That's always the confusing thing with these phase diagrams for me. It says atmospheres, it makes you think about the atmosphere. It's not. It's the unit of atmospheres, which is 10 to the 5 pascals. Pascal is the SI, is the standard unit for pressure. So okay, we can think about that. There's a quantity called the triple point. This is where we can have all three phases of water together in equilibrium. So we can have water vapor, we can have liquid water, we can have ice at this point, the triple point. And if we look to see what temperature that usually corresponds to, 273 Kelvin. So It's about 273 Kelvin, or 0 degrees Celsius. At that temperature, at equilibrium, we can have all three phases of water. So if you have a beaker with liquid water, ice cubes inside, and you close the top of that beaker off and just have water vapour above the surface of the liquid water, the temperature inside that beaker at equilibrium will be 0 degrees Celsius. Okay, that's the triple point. Now the way I like to think about these phase diagrams is what would happen next. So this line is the equilibrium line, and below this line water exists in the form of a gas. Above this line it exists in the form of liquid, except when we go colder than about 0 degrees Celsius, where it changes to ice, which makes sense. So if I have some conditions where my vapor pressure of water is around about 10 atmospheres and the temperature is around 600 Kelvin, all of the water will be in the form of water vapor. We then cool, then I can cross this line and I can have some condensation. It's when I cross this line here, that's when we have some, call it vaporization or condensation. We get some water droplets. Okay, now if the vapor pressure is lower than about 0.01 atmospheres and the temperature is 500, again the water vapor will be in the form of vapor, but if we cool, we'll go straight to the ice phase. So water vapor will condense out instantaneously to form ice. There won't be any intermediate liquid phase. It will go straight to ice. So that's how I like to understand this phase diagram of water. Hope that makes sense. Any questions on that? Is that clear? Okay. So these are some measurements now of different vapor pressures. Don't worry about the units. And these are measurements in the atmosphere as a function of temperature. Don't worry about the different colours either. The interesting point about this is that the measurements never really go above this sharp line here. Why is that? We've got measurements below this well-defined line. We don't have any measurements above this line. Why do you think that might be? Yeah. Supersaturation occurs. Yeah. So I just remembered you did a course last semester, atmospheric physics. Talked about supersaturation. Yeah, okay. So if we go across this line, we start to form clouds. So the water condenses. So any water vapor pressure that's above this line will pretty much instantaneously condense to form liquid water. So I guess the point here is, in the atmosphere we tend to observe that the vapor pressure is never above this well-defined line, but we can often see it's below this line. And I'll talk about that in a minute. I'll talk more about that in a minute. So James has said water has a large heat capacity. We'll talk about that too. It has a large latent heat of evaporation. Do you know what this means? So this is when say water vapor condenses to form liquid water, heat's released. Why is heat released when we have this condensation? Where does the heat come from? Yeah.
Is it from the bonds holding together when ripping apart?
It's the intramolecular bonds that I've just talked about. Yeah. So again, this is about thinking about the gas, molecules moving around really fast. Think about the liquid, molecules not moving around that fast. So if you look at the energy state of the gas, lots of energy. Look at the energy state of the liquid, not so much energy. So there's a difference in energy state. Where does that energy go when we have condensation? It's released as heat. That's the latent heat. And the same is true when we have the phase transition going to ice as well. So the molecules become more constrained, that heat's released in the form of latent heat of fusion, not evaporation. And also, water has a large surface tension, and this is important for cloud formation, which I'll talk about too. So here we're thinking about, what do I mean by surface tension? Oops. All right. Yeah, I normally have a little experiment I can do, but I've not brought it with me today. But if we had a beaker of water, oh, it's supposed to be a beaker, never mind. And we had a pin, a needle, so I'm looking at the needle edge on, so it extends into the page. Then that needle can float on top of the water due to the surface tension. It tends to deform the surface of the water, and we look at balance of forces, so it has weight, so there's a force coming down here, and the surface tension acts to keep this needle above the surface of the water. So it's just a force in the opposite direction. That's due to the surface tension of water, but that property turns out to be important for cloud formation. It holds droplets together. I'll talk about it in a short while. So just a fairly brief overview slide of some of the processes that we can consider, and I won't dwell too much on this. So we've got processes going on in the ocean, we've got evaporation processes, we've got condensation processes, and the heating, the latent heating, when we get condensation. It gets transported, forms clouds. They sometimes precipitate. If the droplets are big enough, they can start to fall through the atmosphere and get to the ground. This all affects the radiative energy transfer, so through the atmosphere. So some of the sunlight can be reflected, some of the heat from the earth can be absorbed and reflected, depends on the properties of water vapour in the atmosphere or of clouds. Snowfall and storage in ice and snow, and surface runoff processes and soil moisture is also important. So these are some of the things we'll be talking about today. So again, I won't talk too much about this, but water has an important role in the transport of elements. The water cycle can partially govern the transport of the other elements. I'm not sure how much of this James, Dr. Allen has covered. So the carbon cycle, the nitrogen cycle, phosphorus cycle and sulfur. And also it can transport dissolved or suspended particulate in groundwater, rivers and oceans. So this is just some sort of general background, and these are some important processes here. And it also plays an important role in precipitation. Now, wet deposition, which refers to rainfall, which then captures pollution particles, aerosol particles as we call them. Precipitation is it's actually the main removal mechanism for atmospheric aerosol, which are pollution particles. There's also some interesting self-regulating systems that we can talk about. So here's one here. We'll talk about this. Plants remove water from the upper layers in the soil, and they return it to the atmosphere through transpiration. But also, the roots of the plants help to maintain this soil. They maintain its integrity. They prevent soil erosion, and therefore they can increase its capacity to hold water. So it's kind of like a feedback mechanism. You see what I mean? So if the plants weren't there, the soil wouldn't be able to hold on to as much water. Plants are there, they can hold on to much water, and the plants can actually use it for their own good. So it's kind of like a self-regulation mechanism. I'm not sure how much James has talked about self-regulation. Has anyone heard of has anyone heard of James Lovelock and the Gaia hypothesis? So this is one of these self-regulation mechanisms. If people haven't heard of that, then I recommend you look up James Lovelock. So Lovelock, just give him a quick Google. Oh, so he's talked about it. Thank you. Yeah, okay. Yeah, it's a good read, so I recommend it too. Okay, so I'm not going to go through this whole slide. Needless to say, there are some direct anthropogenic influences. So ways in which humans can directly influence water in the climate system. So I recommend you read through this slide in your own time. So there are things like aquifer mining, surface water diversion, so changing the path that rivers take, desertification, wetland drainage, soil erosion in agricultural regions, so diverting water, deforestation, cutting down trees, and dam building. So just make sure you understand all of these mechanisms, all of these direct ways in which humans influence the water cycle. I'm not really going to go into that in too much detail, because the main way, the most important ways for this lecture are the indirect ways. So we're going to consider the indirect ways. So this is a table showing, okay, due to these different direct methods for how humans can influence the water cycle, how they're affecting sea level rise. So you can see some of them aren't really affecting it that much. 0.03 millimeters per year due to aquifer mining, for instance. But some of them can influence them by a lot more. So you're looking at that's half a millimeter per year. Might not sound like a lot. It is actually significant. Okay. And here's one fairly recent significant direct influence, which is I wrote it down, it's the Aral Sea in Uzbekistan. Between, I think, 1989 is this picture here, and this is the same picture, the same view from 2014. Now this was just using water for irrigation, just diverting the water for irrigation. You see the significant impact that that's had on this sea. But so on regional scales, direct influences can have a big effect. But on a global scale, which is, I guess, what this course is about, global biogeochemical cycles, they're very small compared to the size of the reservoirs. So the direct human perturbations are fairly insignificant globally. So that's another important point. Okay. So now I'm going to talk a bit more about some natural processes involving water rather than these direct influences. So first of all, I think Dr. Allen has talked about water as a greenhouse gas. Well, he's talked about greenhouse gases in general, he told me. So water structure means it's very effective at absorbing long-wave radiation. Why is that? Well, you think about carbon dioxide, another efficient molecule. What happens is, when we think about greenhouse gases, we're thinking about the absorption of a photon of energy, radiative energy, by a molecule. And when that happens, the molecules start to vibrate, and they vibrate in these different modes. So one mode, the carbon dioxide, is the two oxygen molecules moving apart like this, vibrating like this. And we can have different vibration modes. So water has different modes, so it absorbs at different wavelengths. So it absorbs photons of different energies. Okay. So this slide shows the irradiance in watts per meter squared per micron from the sun, or from an object at 6,000 Kelvin, which is about the temperature of the sun, And so you see the amount of energy that's given off by an object at 6,000 Kelvin as a function of the wavelength of the energy. So you can see the sun gives off shorter wavelengths, centered around about 500 nanometers, or 0.5 microns is the wavelength of the energy. Whereas an object around about the temperature of Earth, it's a little bit cold, gives off energy at longer wavelengths. Okay, and so if we look at the absorption as a function of wavelength, we can look at the absorption for, say, carbon dioxide, and see that the amount of this energy that's absorbed by the molecule is very little at the shorter wavelengths. So it hardly absorbs at all in the visible range. So what happens then is we think about the short waves coming through the atmosphere, which is fairly transparent to the short waves, and then being absorbed by the Earth, increasing the temperature of the Earth, and the Earth itself emitting the long wave radiation, which can then be absorbed in the atmosphere by these different molecules. If we look at the absorption at the longer wavelengths, you see it's much larger. So, but the point about this slide is that water vapour absorbs in different bands than CO2. So there's some overlap, but also water vapour absorbs over probably, you'd say, a larger fraction of the wavelength spectrum. Okay. So I had that little schematic. I don't know how many people have seen this. Maybe I've shown you this before. So it's some cows in a field belching methane. It's the temperature of Earth. It's a power station emitting CO2. Sunlight coming in. Some of it's reflected, by clouds. Some of it gets through, warms the Earth, and then the Earth emits in the long wave. And we can change things like, I've not got water vapour, but we can change, for example, CO2. You see that more absorption takes place. We can change the clouds. You see we get more reflection, and so the temperature goes down. We can change how reflective the clouds are, how white they are, and we get more reflection still. I guess that's kind of related to this slide here. Okay, so Dr. Allen told me he's introduced the concept of forcing and feedbacks. So the IPCC definition, the Intergovernmental Panel on Climate Change, is that right? Yeah. So you know about the definition of forcing from the IPCC perspective is the change in watts per metre squared when you look at the difference between 1750 to the present day. Yeah? That makes sense? Not sure about that. So the forcing would be, for example, you could look at the forcing of aerosol particles, anthropogenic aerosol particles. So how many aerosol particles we've emitted, humans. And what the IPCC do is they look at how many watts per metre squared are reflected or absorbed by Earth in their climate simulations from pre-industrial times, so about 1700s, and they do the same for present day. And then they do the difference, and that's the forcing. The number of watts per metre squared is the forcing. Is that okay? And feedbacks, so I guess the important thing for feedbacks are to know what a positive feedback is and what a negative feedback is. Do you know about that? Yeah, anyone not? Okay. So, what's the point here? So I want to pick up on this second point. So the amount of water in the atmosphere will increase in response to warming. And why is that? Why will the amount of water increase in response to warming, do you think, in the atmosphere? At the back?
Increased evaporation.
Says that there. Yeah. But why? Why does evaporation increase? If it gets warmer, why do you have more evaporation?
There's more energy breaking the bonds between the most molecules.
That's a good point. Yep, yep. The other point is that warm air holds more water vapour than cold air. Did you know that? Let's go back to the phase diagram. Excuse me. So think about it in terms of the phase diagram. This line here is the equilibrium line, and water below this line exists in the vapour phase. Water above this line condenses, it starts to condense. So can you see that warm air holds more water vapour than cold air? Yeah, yeah, you can. So as the air gets warmer, this line goes up. So warm air holds more water vapour than cold air. Okay? And a result of that, so this is considered a feedback in the climate system. A result of that is you have more atmospheric water vapour in the column, in the atmosphere. So therefore we have a greater greenhouse effect. So therefore this is a positive feedback. Does that make sense? Because the warmer it gets, the more water vapour we get. The more water vapour we get, the more absorption, so the warmer it gets. So it's positive feedback. We also have more cloud water because, well, we think we do. I'm not sure this is 100% known, but we think this is what's going to happen. So because we have more water vapour, we might have more clouds, which would probably result in a higher atmospheric albedo, because clouds tend to reflect radiation. They reflect shortwave radiation back to space. And so overall, we think this is a negative feedback because the water vapour gives the positive feedback, but the cloud feedback we think is negative. But again, this is not very well known. It can be positive in places like the Arctic, for instance. And the net water feedback is positive. So we've got both water vapour, this is positive. We've got clouds, which have a negative feedback. The more clouds you have, the more sun's reflected back to space. But if you add these two things together, the net water feedback is positive. But we don't know about the exact overall magnitude. It's one of the biggest uncertainties in climate predictions. Okay. Right, so clouds. So I want to consider the concept of saturation. So if we consider a closed system. So in this closed system we've got water vapour in the form of gas, and we've got condensed water, liquid or ice. And if we have this, it'll form an equilibrium. So what will happen is some of the liquid will evaporate and some of the vapour will condense, and eventually there'll be a point where there's no net transfer from the vapour to the liquid and from the liquid to the vapour. At that point we're at equilibrium. And the gas phase concentration under that equilibrium, you can express it as a mixing ratio if you want. So mass of water vapour per unit mass of air, or you can express it as a partial pressure or molecular concentration, and that's known as the saturation point. So it's the point at which the air saturates. Any further cooling, if you cool quickly enough, will result in some condensation. Okay, does that make sense? It goes back to the phase diagram again. So what will happen if we leave water and vapour long enough at a given temperature is the partial pressure of water will sit on this line at the temperature that we're at. And then any further cooling means we go into this space where we start to get some condensation. So when there's no condensed phase present, so no liquid or ice, which is most of the atmosphere, the vapor concentration can actually be lower than the saturation point. We've not approached equilibrium yet, and therefore we can describe that situation as being subsaturated. So that was this slide here. So this line, this very well-defined line here, we're saturated here. If we're below this line, then we're subsaturated. We're not at the saturation point at that temperature. And so the water vapor concentration for a given temperature and pressure, you can express this as a percentage relative to saturation, and that's known as the relative humidity. So you take the partial pressure of water and you divide by the saturation point, and that tends to be a number that's less than 1. That's known as the relative humidity. You're expressing the humidity relative to saturation. It's a relative humidity. Okay. How to make a cloud. So very simplistically, moisture will evaporate at Earth's surface, and it can be carried vertically upwards in what we call an updraft. And as it does that, pressure decreases the further up you go, because pressure is just the weight of the air above in the atmosphere. So as it does that, the air cools down. Why does it cool down? Why do you think the air cools down as it goes up through the atmosphere? Yeah, Anna. Yeah.
It expands.
Expands. Yeah, that's okay. So it expands. And it's due to conservation of energy. So if you think about it in terms of the molecules of gas in a parcel of air, in a balloon, let's say it's in a balloon, air goes up. What happens? That balloon expands. We can think of the molecules inside the balloon pushing on the edges of the parcel. So they're actually doing work to expand the parcel. They're doing some work, and to do that work, energy must come from somewhere, and it comes from the internal energy of the gas. So the molecules slow down, and the temperature of a gas is related to the speed or the kinetic energy of the molecules. So that's why when a parcel of air goes up through the atmosphere, it cools down. Due to conservation of energy, and as it cools, the saturation point decreases. Warm air holds more water vapour than cold air. Cold air holds less water vapour than warm air. I said that right. So therefore, at some point, the air will approach saturation, which is 100% RH, and RH equal to 1, relative humidity that is. And when it reaches this temperature, where the RH is equal to 1, that's known as the dew point temperature. And it can become slightly supersaturated, and so it begins to condense out to form liquid phase. Right, I'm just curious, has James showed you this experiment? Has anyone seen this experiment before? You've seen it? You've seen it, okay. Right, so I'm just going to show you a quick demonstration of how clouds form using this. It's a cloud chamber. So what is it? There's a valve here, it's just a washing machine valve, but it's good enough to hold the air in. And there's a bike valve here, so I can pump air in, and this thing here is just if the pressure gets too high, it will release the pressure. So the first thing I'm going to do is open this up. I've closed all the valves. I'm going to put some water in there. I don't have to leave it very long until it forms an equilibrium. Oops, see that? Quick hands. Okay. Close it up. give it a shake. So there's a water coating on the walls now, and what that water's doing, this is a closed container, so the water's evaporating until we've got the saturation point inside. So any further cooling should form a cloud. The way to do that, I'm going to cheat a little bit. I'm going to pump air into this container. So the same's true. We've got saturated conditions. We've got more pressure inside than outside. If I open this valve, the air inside will do work against the air surrounding it. So it should have a drop in temperature, and we should see condensation and see a cloud forming. We actually don't see it. The reason why is because, does anyone know? I know you. Go on. Aerosol particles. So I'm going to make some aerosol particles with a match. So all I'm going to do is repeat the experiment, but before I do, I'm going to strike a match and burn it inside the container for a short while, and that generates like billions of small aerosol particles. So these pollution particles, smoke particles, they're one type of aerosol particles. There are lots of different types, and James can tell you all about those. Okay, so again, let's repeat the experiment. So the same's true. The only difference is we've now got our cloud condensation nuclei. So repeat the experiment. Let the air out. Did you see that? So we saw the condensation there. Just because we have the condensation nuclei, the small aerosol particles, for the water to gather around. Okay. In the case where we had no aerosol particles, we had a very high supersaturation. So water, it just existed in the form of vapor. So it shows that it's not only the phase diagram of water that's important, but it's also these things, these cloud condensation nuclei, that are important, that are in the atmosphere everywhere. They're important for cloud formation. Okay, latent heat effects. So here, just to say, water has a high latent heat of vaporization. So that means when we formed the cloud there, latent heat was released and warmed the air somewhat. It didn't warm it. The net effect was to cool the air, because we had the air doing work against its surroundings. But in the case where we had the cloud, the air was just a little bit warmer than the case where we didn't have the cloud, due to this latent heat of vaporization. And the evaporation of water from the ocean surface and condensation of cloud droplets at altitude is an efficient method of transferring heat from the ocean to the atmosphere. And this heating of the atmosphere can actually make the air more buoyant and promote more convection and more cloud formation. You can get things like very deep thunderstorms due to this method. And this is a positive feedback too, another positive feedback. So we're releasing latent heat, that's creating more convection. And this is the mechanism by which tropical cyclones, so hurricanes in the northern hemisphere or typhoons in the southern hemisphere, these are types of tropical cyclone. That's the mechanism by which they form, and they're powered by heat from the oceans. So yeah, so this is the slide about cloud condensation nuclei. So this is kind of James's field, aerosols really. Turns out that it's the larger aerosol particles, which are typically in this size range, 50 to 100 nanometers, which are composed of soluble material, so for example sea salt or sulfate. They're more effective as cloud condensation nuclei. they can form cloud droplets more effectively. And they're known as cloud condensation nuclei, or CCN. And so this is just reiterating really, when a rising air particle reaches a certain supersaturation, the CCN we'll say they activate. It means they start to take on water. It means the water starts to condense onto them. And yeah, okay, so they take up water vapor and they reduce the water vapor content. So if you were to measure the amount of water vapor in the air, that would actually go down. It's just because it's changing phase, it's going to the cloud phase. And this is what happens at cloud base. You see cloud base, so you've got that change between constant water vapor. When you get into cloud, the water vapor starts to go down that way, and the cloud content starts to go up. And if you add the two together, they'd be conserved. They'd be equal to the same value they were below cloud base. The remaining particles that don't activate, that don't form clouds, they're known as interstitial. That's this word here. It's a bit of a complicated word. I don't use it, but anyway, some people call it interstitial. Aerosols that don't really interact with the cloud. Increase in the number of CCN, cloud condensation nuclei. So, for example, due to anthropogenic emissions, cars, power stations, so on, agriculture, that will increase the number of cloud droplets too. So you saw in the little experiment there, the more aerosols you have, the more clouds you have. The thicker the clouds. It'll decrease the amount of water per droplet. So why is that? Why does it decrease the amount of water per droplet? Does anyone know? So there's a fixed amount of water in the cloud, but there are more droplets. Therefore, fairly obvious, the size of the individual droplets, as we increase the aerosols, the size of the individual droplets must go down. That has an important effect. So a little schematic here. So this is just a little drawing looking down on the ocean, and we've got a cloud over the ocean. So these are the cloud droplets. Clouds because they're white. So we've got a given number of cloud droplets here. Now what I'm going to do from the left to the right is increase the amount of cloud droplets, but keep the total volume of those droplets the same. And what do you notice happens? If you were to stare at that for a bit and tell me what the average colour is, as you look at it, as it goes from left to right, what would you say? The average colour tends more towards blue to white. It goes from blue to white. If you wanted to keep cold on a summer day, what colour t-shirt would you wear? White. So therefore, the more aerosol particles you have, the more reflective the clouds are, the more sunlight they reflect. So this is why the anthropogenic aerosol effect is a positive forcing. It's more sunlight being reflected, or negative forcing. More sunlight being reflected back to space due to anthropogenic aerosols. Okay, so just to go through this fairly quickly now before we have a break. So precipitation. So just simplistically, precipitation particles, these are particles that start to fall from clouds. They're known as hydrometeors. Hydro, water, meteors because they fall into Earth. Cloud droplets, they're starting to fall in a cloud. They fall very slowly under gravity. But if a small droplet falls below cloud base, it will evaporate very quickly because it's dry below cloud base. So you need bigger droplets. You need really big droplets before they're going to get to the ground. So larger particles, they'll form much faster and they take longer to evaporate, and this is what forms rain. And so how does this happen? Well, cloud droplets will start to coalesce. They start to touch each other, join each other, and form larger droplets, which can then fall faster. Cloud droplets themselves, as they form from condensation, they can't grow to sizes big enough to start to fall as rain. So it's this coalescence process which leads to rain formation in warm clouds. And I think there's an animation. Yeah, they start to coalesce. You see that? Should put that up there. Yeah, okay. Start to coalesce, get bigger, start to fall, and they sweep out other cloud particles below. So fairly straightforward. And they eventually fall as drizzle. Now this can happen in shallow clouds, it can happen in deep clouds too. But shallow clouds, very thin clouds, can still be thin enough that this process can happen and lead to rain. Ice clouds. So what temperature does liquid water freeze at? 0 C. Actually it doesn't freeze at 0 C. Pure water doesn't freeze until we get to minus 35, believe it or not. And if it does freeze, but it does freeze at temperatures between 0 and minus 35 in the atmosphere. And that's because we have these, like for warm clouds, cloud condensation nuclei, but for ice clouds, we have special particles which are called ice nuclei, or ice nucleating particles. Ice nuclei here, or IN. And these are quite special particles. Only it's about 1,000,000 times the number of aerosol particles can be ice nuclei typically. So take the aerosol number concentration in the atmosphere, if you count up how many aerosols there are, divide by 1,000,000, and that's typically your number of ice nuclei. For example, dust and bacteria make very good ice nuclei. Dust in this context might mean, for example, desert dust. So desert dust which is swept into the atmosphere by strong dust storms and transported across the globe. These can be good ice nuclei. And because ice is a more stable form at temperatures below the triple point, below 0 C, if ice nucleation is initiated by these ice nuclei, water tends to rapidly transfer from the vapour, and liquid particles will evaporate and it will all go to the ice phase. So once we nucleate ice in a cloud, it tends to grow at the expense of the droplets. The droplets tend to evaporate and we tend to get snow. And the process of converting water, a water cloud, to an ice cloud, we call that glaciation. And glaciation can often be another trigger for precipitation to occur. Here's one mechanism by which it can happen. Oh, so yeah, this is mixed phase cloud. Okay, yeah, there they are. So mixed phase cloud. In an updraft, we have some CCN, cloud condensation nuclei. They activate to form liquid droplets, and as the air rises, the ice nuclei will activate to form ice crystals. So some of these form ice crystals. These are supposed to be ice crystals here. And then water is transferred to the particles from the vapour. The ice grows faster than the liquid. The liquid evaporates in this situation. So they grow very big and they're more likely to fall. Once they grow to big sizes, they're more likely to fall. And they can also stick together and form snowflakes. So we have lots of ice crystals, similar to the formation pathway for drizzle, precipitation for drizzle. We can also get snow precipitation by this mechanism. Incidentally, this process can happen high up in the atmosphere, and it can lead to precipitation. It can lead to the initiation of precipitation in the ice phase, but eventually, if the temperature is warm enough at the ground, this precipitation can then melt on its descent and fall as rain. So you tend to find the ice processes can be important to initiate precipitation, but it can still form as rain. Actually, globally, we think 50% of the precipitation forms via the ice phase and 50% by the warm phase, by the drizzle phase. There's another precipitation category, we call it whirlpool. So if supercooled water that's cool below zero, touches ice, it freezes on contact, and if a large ice particle is in an updraft carrying small supercooled water droplets, it will form a large ball of ice as it gathers up water, like a hailstone. We call this whirlpool. And strong updrafts can produce the largest whirlpool. That's because they can become very big. So if they're going to stay lofted, you need a strong vertical motion in the atmosphere, some strong convection to keep it up there. Okay, now I'm going to skip through a couple of slides. I'm going to skip through this slide, so feel free to read through this one in your own time. Yeah, and skip through this. I want to get on. Right, so just have a read through those few slides yourself. So they're just examples of what scientists think are happening today and affecting climate change from the point of view of water interactions. So have a read through that yourself. So two things I want to talk about before the end are ways of modifying clouds. So there are two ways in which humans deliberately modify clouds. One's known as cloud seeding. So in this mechanism, there's a big research program in the United Arab Emirates to try and have clouds rain more, obviously for water supplies and so on. And so the way this works is they use aircraft, or they can use rockets to fire silver iodide particles, which are very good ice nucleating particles, into the upper layers of clouds, obviously using planes or rockets, and this initiates glaciation and precipitation. Okay, so you can't make it rain obviously when there's no water, but it can be used to cause a rain cloud to rain more over a particular area. Okay, so this is due to the ice precipitation pathway that I mentioned before. Just want to show you a quick slide on some observations I made in a field program a few years ago. So this was a field program, and this is the west coast of Chile here. And in this part of the world, we get these clouds, these very thin clouds called stratocumulus clouds. They're very thin. They're about a couple of 100 meters thick in the atmosphere, and they're probably about 1 kilometer above the ground, above the sea in this case. You can see them from satellite, and yeah, don't worry about the title here, there's something else. So one thing you can see in this slide, if you look at the animation, you can see these straight line features. Can you see them? Is it showing up on the animation there? So what do you think they are? Yeah. They're ship trails. Yeah, they're ship trails. So what's happening there? So why can we see them? Almost, but not quite. Anyone else? It's not seawater. it's just the pollution coming out of the stack. So it's just the exhaust from the ship. That creates very small aerosol particles which get lofted into the cloud and are forming and are basically acting as cloud condensation nuclei. And so what we see from satellite is the clouds appear brighter in those regions. Why do they appear brighter? Why are they brighter? At the back? Oh, sorry.
With more aerosols, more condensation nuclei formed,
Yeah.
and therefore more droplet.
Yeah. So it's going back to this slide here. More aerosol particles, the brighter the clouds get.
Yeah.
So the other method that humans deliberately modify clouds is well, they don't do this yet, but this has been proposed. It's known as the cloud brightening scheme for geoengineering. It's a geoengineering technique, and it's proposed that we provide more cloud condensation nuclei from marine stratocumulus from seawater. So rather than using the combustion sources, actually sucking up the seawater and generating sprays, which then get lofted in the thermals and find their way into clouds and make the clouds brighter. Okay, so this should increase the droplet number in these regions, make them brighter, also increase the cloud lifetime and the cloud albedo, how much is reflected back to space. And given the short lifetime of water, you talk about reservoirs, turnover times, it has a short lifetime in the atmosphere, it can be switched off at fairly short notice compared to other proposed geoengineering techniques. So what do you think about that? Should we have a discussion? Is that a good thing to do? Yeah.
What if a wave hits it?
The ship?
Yeah.
Yeah, they don't look very stable, do they? I mean, I guess this is an artist's
It's like quite
impression.
top-heavy.
They do a bit, don't they? Yeah.
I don't know if people did that, then everyone would be like, oh, it's okay, we've got geoengineering techniques that will mitigate it rather than stopping investing stuff that will stop it at the source by not burning fossil fuels anymore.
Yeah, it's a good problem. It's a good question. Good point. Sorry. So I've written down here. It doesn't actually solve the problem, which is the increased CO2 in the atmosphere. You're not actually taking the CO2 out. You're not reducing the CO2. You're coming up with another mechanism to reduce the global temperature. Any other comments? Yeah.
Are there going to be any repercussions for adding more clouds into
Yeah. So I've got written down a point here. These stratocumulus clouds, they only really form in large areas in certain parts of the globe. So it might be that you're able to create local cooling in different places. It's like a regional cooling rather than global cooling. And what would that do? It's going to affect atmospheric circulations. Yeah, could cause a drought in one location or flood in another location, for instance. So, yeah, another good point. Any others? Yeah.
Are you able to send those to the slides?
Oh, yeah, I can send you that. Yeah, I'll send you that. Yeah, no problem.
The
Yeah.
slides are on the
I don't think those two slides are, so I've just brought them along. You know, the animation one and the cloud one. Yeah, so I can email that to you. Yeah, any other points? Oh, yeah.
I just think in general, environmental systems are quite sort of, not necessarily fragile, but dynamic. And if you change one thing here, like it's having a local effect that maybe isn't obvious now, but somehow maybe it will change the ecology.
Yeah.
It will change this.
Unforeseen ramifications.
Yeah.
Yes.
Stuff that maybe you can't predict, but later on.
Yeah, so I did some like preliminary analysis on this, and do you know how much it costs to make these ships? Unbelievable. If you look at the cost benefit, so obviously there's the Stern report, the Stern review, which talks about the cost of an increase in temperature of a few degrees, but the cost it takes to make these ships is like 10 times more that cost. So I think you've got to do the cost benefit to I'm not an advocate for this, by the way. I've done research in this area, but it's not something that I'd say we should be doing it. Yeah.
Just a question. What is like the main particle in the sea that is
Salt. Yeah. Sodium chloride. Oh, it wouldn't be an ice nuclei. It'd be this is for cloud condensation nuclei. Yeah. So the silver iodide is to form glaciation in the deep clouds. Yeah. This is to. Yeah, this is just for clouds. Yeah. Yeah. So James will talk to you about a lot more geoengineering projects, I'm sure, but this is just the clouds one. Okay, break time. So is it normally a 10-minute break? Come back and I'll go through some questions. Yeah. Sound good? Okay, so what time are we on? 5 past. So we see you back at quarter past 4. Yeah, 4:15, back here. And I'll go through some questions. So some example questions. Yeah. Yeah. No, I haven't. Changing that.
I want to ask that water has four kind of two kind of vibration waves and two kind of rotation waves.
Say what was the question? It's got these different modes of vibration.
Yeah. So what does it result in?
Oh, well, that results in the basic result is the absorption dependence on wavelength. So some of these will be due to sort of vibration, and some of them will be due to rotation. And you could have different frequencies too. So you could have if it vibrates at one frequency, it can't always vibrate at continuum frequencies. There are very specific frequencies that it can vibrate at, and so but there's a probability of vibrating at these different frequencies. So then if you increase the energy, say by a factor of 2, so the wavelength, so the frequency by a factor of 2, so you decrease the wavelength and have a higher energy photon, then you might be able to get, for example, twice the frequency but the same vibration. But that all results in this absorption as a function of wavelength. This is the important thing. You don't really need to know the details of which vibration modes and which rotational modes this corresponds to or this corresponds to. I don't know which one it is. Just need to know that it has this, it has an absorption spectrum which is significant. It absorbs at wavelengths that CO2 doesn't.
And another question, why dust is
Yeah, so with the bacteria, we think that's due to the protein structure being quite similar to the structure of ice, the crystal structure of ice. So we think that the long chain proteins within the bacteria are so similar to the structure of ice that water molecules can condense onto those structures in the same way that they can ice, and if they do that, then ice can deposit on top of that. And it's similar for dust. So dust tends to be mineral composition. We think minerals. So things like quartz, things like feldspars, all of these minerals, and they have cleavage. They have morphology at the microscopic level, which is quite similar in size to the structures that you find in ice crystals, and that's why they do this one. Yeah. I haven't got it. I forgot. Oh, so if you want to go to that web page, those two slides from there. So you just type in 130.88 .66.124/James. 130.66. James. Okay, so someone's just, before we start on going through these questions, these numerical questions, someone's just asked me a very good question actually. So it was this slide that I want you to read through yourself, but maybe we'll read through it now. So cloud, aerosol cloud, climate processes. So increasing the number of CCN, cloud condensation nuclei, increases the number of cloud droplets. So we know about that. And it decreases their size and it increases the albedo, the whiteness. So that's the slide that you saw where we were looking down on the ocean, left to right. And so this has a net cooling effect on climate. And sulfur aerosols are quite good CCN. So that's probably why the matches are quite good. It's the sulfur in the match head which acts as a CCN. And so James will talk about that later. But then this point here, black carbon can suppress cloud formation by causing atmospheric warming, and this is a net warming effect, but it's not thought to completely offset the cooling effect globally. And I think, if I'm right, I think the question was in a previous slide, I just said that in a warmer climate you get more water vapour, and so it's a positive feedback and you can get more clouds that way. But I'm saying that black carbon suppresses the clouds because it goes warmer. So that's a good one, isn't it? Does anyone know why? Yeah.
Is it to do with the altitude of the
Might be. Might be. Yeah, I think you could argue that. Any other comments? So it does seem to be a contradiction. I think, I'm fairly sure. So if you have black carbon in the same place as the cloud, so it's just kind of, you've got a cloud and black carbon mixing into the cloud, then we can apply the phase diagram of water. Where was it? So let's say we're at this temperature and we've got a cloud, and then we mix some black carbon into that cloud, and the black carbon, what that does, because it's black, it absorbs radiation. It absorbs the shortwave radiation and then it re-radiates it and heats up. So we move to the right. So we move into the part of the phase diagram where water exists as a vapour. So that makes sense, doesn't it? Now, when we're talking about all these climate interactions, it's very, very difficult to get your head around sometimes. When we're talking about, where was the other slide? Wasn't here, it was here. When we're talking about the forcings and the feedbacks, so the amount of water in the atmosphere will increase due to warming. It's a question of time scale. So what happens here happens over a much longer time scale. When we think about individual clouds and black carbon, it's quite a short time scale thing. Typically on the time scale of a cloud, a day or so, or less than a day, half a day, whatever. When we're talking about this feedback, this climate feedback, this global climate feedback, what we're talking about is it's getting warmer over a long period of time, which affects the evapotranspiration rates, and so more water vapour enters the atmosphere. On the time scale of a cloud, if we've got some local warming, there's not enough time for that to affect the evapotranspiration rate at the surface. You see what I mean? So this is the black carbon also tends to produce localized warming effects. So it might warm in a particular layer in the atmosphere rather than the whole atmosphere. Does that make sense? So it's a quite complicated explanation, but it's a good question. Any other questions? Okay. So these are the example questions that James asked me to go through. Do you all have these? you have these on Blackboard? Do you have the answers on Blackboard? Alright, okay. I have the answers. Right, so the first one. So this is past coursework from 2009. So first one, it says question A. So what is the definition of a residence time when applied to a reservoir in the Earth system? Anyone want to start with that one? Yep.
Isn't it the time it remains within said reservoir between its time input and when its output occurs?
Okay, so the residence time, so
It's like a fin sign.
well, this tau,
Yeah.
yeah, so something to do with time. And I've got residence time, it's defined as the burden divided by the sum of the instantaneous sink fluxes. So it's the amount you've got,
Yeah.
symbol M, divided by the sink. Okay, so M, you see that up there? Yeah. M divided by S. He's given it a subscript. Oh yeah. So the sum of all sinks. Do you know what this sigma symbol means? Yeah, it just means sum all of the sinks. Sum them all up. So add them all up. So if you've got two sinks, S1 and S2, add them together, and that's your sigma SI. So I guess you could think about that in terms of if you've got a sink of water with a plug hole, and you take the plug out, and your flux out is S, and you've got M in there. So the time it takes, so if S is measured in, say, meters cubed per second, and M is measured in meters cubed, then the time it takes for this sink to empty, tau, is going to be M divided by S, and that's going to be in units of seconds. Make sense? Okay. Right, so question B. So a system has a burden M and known sources, which are Q1 and Q2, and known sinks S1 and S2, and it's asking you to sketch the system and write an equation for the rate of change of the reservoir burden as a function of sources and sinks. So with this one, so the diagram's fairly straightforward. We've got our burden M, and we've got two sources and two sinks. So you could just draw the sources going in, Q1 as arrows, Q2, and you could draw the sinks coming out, S1, S2. So that's our little sketch. Makes sense. And now says write an equation for the rate of change of the reservoir burden as a function of the sources and sinks. So how do you think we go about this one?
I need to know the order of the sink of the things.
So who's talking? Oh yeah.
Do you not need to know the order of it?
The order.
Yeah.
So what do you mean?
So how the total burden changes as a function of what's already in it. So it's like 0 at 4 first or...
Oh, as James talked about that, time dependent
Yeah.
rates of change. Okay. I guess you would. Yeah, I guess you would. But for this one, I've looked at the answers and it's a first order rate of change. So yeah, do you want to, anyone?
Would
Yeah.
it be the sum of all the sinks?
Sum of all the sinks. So Q1 plus Q2.
Minus the
Yeah. S1 minus S2. And what's that equal to? So it's just equal to, it's the rate of change, dm by dt, yep. So that's fairly straightforward. It's just asking you to write that down. So I guess it's starting off fairly straightforward questions, and then I think we start to get a bit more complicated now. Part C. Right, in the above system, so the system we've just been talking about, the two sinks have been measured to be 50 teragrams per year and 100 teragrams per year. And the two sources have been observed to be 100 teragrams per year and 20 teragrams per year. By how much would you expect the amount in the reservoir to change in the coming year, and in which direction? What do we think? So Q1, what's that, 50, we'll call that 50 teragrams per year. Q2, 110. S1, is that 100? Yeah. And that's 20 teragrams per year. So how much would you expect the amount in the reservoir to change in the coming year, and in which direction? How would you go about this? Yeah? You put your hand up. What would you do?
You add the sinks together,
Yeah.
then add the sources together, find the difference, and whichever one's bigger, that's the direction it's going.
Yeah. Again, so you just put it in this equation. Hello. Have I done it the wrong way around? Sorry, what? Oh yeah, sorry. Yeah. So that should be S, should it? Yeah. Yeah. I was gonna start off wrong and then write down the right answer. It's good, isn't it? Because I've got the answer there. So Q1, yeah, that's Q. Yeah. So add these up. 120. That plus that. Minus 160. 110 plus 50. So it's minus 40. Is that the answer? Yeah. 40 teragrams per year. Are you sure I've done that right? In the bus system, the two sinks have been measured to be 50. No, you are right, but the answer's wrong. So yeah, I guess we'll need to change that. So does James make the answers available later on Blackboard? Okay, I'll ask James about that one. But yeah, so 40 teragrams per year, yeah.
On the agreement that you've got, is it meant to be sink 1 plus sink 2?
Say again?
Is that meant to be sink 1 plus sink 2?
Is this meant to be?
The equation in the rectangle.
Isn't it meant to be Q1
Oh, okay.
plus Q2 and get a bracket?
Yeah, I mean, if you put that in brackets, then that would be a plus.
Okay.
Is that okay? Can I turn over?
So
Yeah.
if it's minus, it means it's going in the direction of the sink, right?
Yeah, minus is the sink. Yeah. So overall, this is a net sink.
Yes.
Yeah. Okay. So part D now. So this one is a bit confusing. Oxygen is formed by photosynthesis according to this reaction. But do remember the CH2O is not the actual formula for biomass. All James has done is he's scaled this by a factor of 6, it's just divided by 6. Because glucose, which is like biomass, is actually C6H12O6. But this equation, this chemical equation, is in the right proportions for each element. So that's the point James is getting at here. So this primary production pathway produces 70 petagrams per year of organic matter. This is the organic matter. And most of this is decomposed and it returns carbon dioxide back to the atmosphere. So this is just one pathway. However, and so he's saying, let's say 0.16% of the primary organic matter is buried in marine sediments. Calculate the oxygen input into the atmosphere resulting from this process. This confused me. It confused me because I thought, well, okay, so this biomass is going to go into sediments, and so the oxygen's kind of lost. But then that, and so James is talking about an input into the atmosphere. But surely, if the biomass finds its way into sediments, then the oxygen would not go into the atmosphere. So I think it's just the wording thing. An input, it can be a negative input. It's just the oxygen that wouldn't be there due to 0.16% of the biomass being taken away. Does that make sense? Well, think about that for a minute. So we've got this biomass. Let's write it down. So we've got CO2 plus H2O plus, gives O2 plus CH2O. So this is the biomass that James is talking about, biomass. And he's saying that most of this then goes on, I guess, to produce oxygen, half a mole of oxygen, and other stuff. What does it say? Sorry, I've got this wrong. It releases CO2 back to the atmosphere. CO2 plus water. Okay, and I've not got the moles, I've not got the number of moles quite right there. It doesn't matter. But what James is saying is if we were to take away 0.16% of this biomass, and just take it away and it gets buried, it's locked away, then it can't produce CO2 and H2O. Okay? And so, do apologise, I've got that confused. Let's start again. Write it down again. CO2 plus H2O gives me oxygen and CH2O. Now this goes on to give me CO2 and H2O. That's what it says. It says most of this is decomposed, returning carbon dioxide to the atmosphere. And it says, however, if around a small percentage of the primary organic matter is buried away in marine sediments, calculate the oxygen input into the atmosphere due to this process. So what he means is, because we're taking this away now, we're taking 0.16% of this away, so we're going to have 0.16% of the oxygen not being able to react with the biomass in the atmosphere. So that's kind of like a source of oxygen in the atmosphere. Does that make sense? Because you're leaving it, it's not reacting with the biomass that's there, because you're taking the biomass away so it can't react. Does that make sense? So it is, you can think of it as an input to the atmosphere, even though it's something that it's just not reacting. It's just the oxygen that's left in the atmosphere, but it's still like an input. Okay, right, we're on the right track. So in that case, what do? So we take our 70 petagrams, 70 times 10 to the 15, and multiply by 0.16%, so it's 0.0016 is 0.16%, 0.16 divided by 100, and that gives us, this is grams, this should give us 112 petagrams per year. So this is the biomass, the organic matter, which is equal to, because peta is 10 to the 15, tera is 10 to the 12, so this is equal to 112 teragrams per year. And that's the organic matter. So then, this is the organic matter that finds itself in sediments, and it's a mass. And these chemical equations, they always apply to number of moles. So we can do things like, if we've got 1 mole of molecular oxygen, that will react with 1 mole of biomass. We could take ratios like that. So the easiest thing to do is convert this mass of biomass, to number of moles now. And to do that, I need to know the molecular weight of the biomass. So what's the molecular weight of CH2O? And so how can I do that? Have you worked it out? Did someone say it? 30 something? 30, yeah, 30. Sorry, I'm going deaf in my old age. 30 grams per mole. So 30 grams per mole is the molecular weight of this biomass. So then I can convert this many teragrams to a certain number of moles per year. And I do that by dividing by the molecular weight. So I take my 112 and divide by 30, and that will be teramoles per year. So that works out to be, so we do 112 divided by 30, works out to be about 3.73 teramoles per year. And remember, this is the number of moles of biomass that finds itself in sediment. So now we need to work out how much oxygen that would correspond to in this reaction. So where do I go from there? Put your hand up. Yeah.
Would you divide by 16 grams per mole? Because you only want the oxygen bit, and there's only one oxygen, so that is weight approximately 16 or 15.
So divide by 16. Why would it divide by 16? Would you say 2 times that? It's molecular oxygen. So I want to know how many moles of oxygen this would react with. Yeah.
Do you times it by 16 or 30?
Not quite. Yeah.
Isn't it a 1-to-1 ratio, so it would react with 3.7?
It's a 1-to-1 ratio, yeah. Yeah, it's a 1-to-1 ratio. So 1 mole of oxygen, molecular oxygen, reacts with 1 mole of biomass. Okay? So the number of moles of oxygen that will correspond to 3.73 teramoles per year. So moles of oxygen, 3.73 teramoles per year. Now the question's a little bit ambiguous because it doesn't, you could end it there. It doesn't actually, I don't think it asks for the oxygen mass input into the atmosphere. So I guess you could end it here, but I think part of this course, within this course, you're always dealing with either masses or volumes. Am I right? Is that right? So it makes sense that the next step would be to convert number of moles of oxygen to, grams or kilograms of oxygen, which is what James has done. So in order to do that, what happens next? What do I do next? Yeah. Times by the molecular mass, which is
16.
no.
32.
Yeah, 32. Twice times 16. So 3.73 multiplied by 32 works out to be, and that's tera, works out to be, and the answer is about 100, it's 119.5 teragrams per year. Okay. So that's like an input into the atmosphere because it's oxygen that's not taken away with the biomass. The last question. Which is the increase calculated above would give rise to an increase in the concentration of oxygen over a long period of time, geological time, which has not been observed, and the process responsible for this is atmospheric weathering of rocks, which uses up the oxygen essentially. So it says approximately 20 grams of oxygen per kilogram of rock is consumed in this process. And so the other piece of information, sediments are formed from the weathering of rock, and a calculated sediment accumulation of this many grams of rock is formed over the last 90 million years. And so we can use this to derive a weathering rate and hence calculate the oxygen loss by weathering. Okay, so that's quite a wordy question. So first thing, the easiest thing to do is calculate the weathering rate. So we take our reservoir equation, we just take the burden, the 18 times 10 to the 23 grams, and divide by number of years, 90 million, 90 times 10 to the 6 years. That works out to be so it's 20 times 10 to the 15, and that's grams per year. And we can also call that 20 times 10 to the 12 kilograms per year. Just taken 3 off there, divided by 1,000. And so the other number to use is approximately 20 grams of oxygen per kilogram of rock is used. So because we've got the kilograms of rock per year as a weathering rate, we can just use this number, multiply this number by that 20 to get the oxygen consumed, and it works out to be, so 20 times 20 10 to the 12 is 400 times 10 to the 12, which is 400 teragrams per year. So that's just that 20 times 10 to the 12 times the 20 grams of O2 per kilogram. Okay, so this is like a sink of oxygen due to the weathering of rocks. And then the question here is this reasonable? Is this in reasonable balance with the oxygen loss to marine sediments? So the answer we had there, remember, the answer we had to the previous question, I think was about 120 teragrams per year. And here we've got 400 teragrams. So we've got removal of oxygen due to the biomass being locked into marine sediments, and that was 119.5 teragrams per year. And we've got the weathering of rocks, which removes 400 teragrams per year. So is that in reasonable balance? What do you think? In other words, does that number equal that number? Does it? It does. That's terra, that's terra. This course is about order of magnitude, so it's about right. So the answer James has written down is this is within an order of magnitude of the other flux. Given the uncertainties involved, this is comparable. A factor of 4. Factor of 4 is less than an order of magnitude. Okay. So I've just realised there's another couple of questions here. I don't think we're going to get a chance to go through all of them, so I'll pick and choose. So I'll go through question 2. Oh, well, question 1, I have to write this down anyway because it's related, follows on from it. This is about phosphorus recycling, cycling within a lake. So we've got our lake, and it has a stock of phosphorus, M1, and there's two sources. There's Q1 and there's Q2 going in, and there's one sink, S1. Okay, so question 2 in this case. So this is the concentration of phosphorus in the downstream river. So what are we saying? The downstream river, it's this one. Downstream river. And we've got an upstream river. And what else have we got? Surface runoff. So that's the kind of situation we're modelling here. And so it says the concentration of phosphorus in the downstream river is this. So that's 0.3 milligrams of phosphorus per litre of water. And it flows at a mean rate of 3 meters cubed per second. And the upstream river, so this is a downstream river, so this is S1, and it's 3 meters cubed per second. And then the upstream river, Q1, says 0.15 milligrams per litre, and it flows at a rate of 2 meters cubed per second. So what's that saying? If you were to measure the concentration of phosphorus in this downstream river, it would be 0.3 milligrams per litre in the water, and the flow rate of water is 3 meters cubed per second, and similar for the upstream river. So assuming that the system is in steady state, what flux of phosphorus does the lake receive from runoff? So this is quite a tricky one. So the first thing to do is to figure out what the sink of phosphorus is, S1, and then the second thing is to think about what the source of phosphorus is. So what do you think? How do you think I would do that? So first of all, how would I calculate how much phosphorus is leaving this lake? Hint, I use these two numbers. Multiply them together. Let's see what happens. 0.3 milligrams per litre multiplied by 3. Now metres cubed, 1 metre cubed is 1,000 litres. So, and this number's in per litre, so I'm going to want this number to be in litres per second. So it's 3,000 litres per second. You can see the litres are going to cancel. So it leaves me with 0.3 times 3,000, which is 900. Milli, so divide by 1,000, so that ends up being 0.9 grams per second. So that's how much phosphorus is leaving the lake in this downstream river. And then the source, the upstream source, I can calculate a similar way, 0.15 times 2,000, and then divide by 1,000, and that works out to be, I've got written down here, 0.3 grams per second. So S1 equals 0.9 grams per second, Q1 equals 0.3 grams per second. And then the question is, assuming that the system is in steady state, what flux of phosphorus does the lake receive from runoff? So how do you think I answer that?
Well, does steady state mean that the limits are equal to the sources?
Yeah, what goes in must come.
So if you use dm by dt, like
Yeah,
that
yeah,
equation,
yeah,
well,
yeah.
just put all the numbers in and then
And set, what do you set dm by dt equal to?
so you use some of the things, but you like put x, like
So dm by dt, what's that equal to? Numerically? 0, yeah. Steady state means nothing's changing with time. So basically, Q1 plus Q2 equals S1. Sources equals sink. And so plug the numbers in, rearrange for Q2, and you find Q2 equals 0.6. Okay? It's a long lecture, this, isn't it? I think question 3 will be important. So one more, and then I'll let you go. So, yeah. Sorry about that. So question 3. So the lake is 1.5 kilometres long, and it's 0.2 kilometres wide, 5 metres depth. If we assume that the lake is well mixed and the phosphorus concentration downstream river is representative of the lake, what is the overall dissolved phosphorus burden and the corresponding overturning of the lake, overturning time of the lake? So with this one, I'll go through it fairly quick. Just calculate the volume of the lake, 1,500 metres, 200 metres, that's 0.2 kilometres, by 5 metres depth. 5 metres depth. That works out to be, multiply those numbers together, you get 1.5 times 10 to the 6 metres cubed. And so the burden of the lake then, no, the mass of phosphorus within the lake is the volume of this lake, 1.5 times 10 to the 6 multiplied by, and so we had 0.3 milligrams, 0.3, so it's representative of the downstream, so it's 0.3 milligrams per litre, which is actually 0.3 grams per metre cubed. Works out to be the same. You've got a factor of 1,000 there, factor of 1,000 there. So multiplied by 0.3 grams per metre cubed, metres cubed, they cancel, works out to be about 450 kilograms. So within this lake we've got 450 kilograms of phosphorus. And so to get the overturning time,